So this is a video for my extended curriculum students, trigonometry without right angles. So you've got the three trigonometric ratios you should be familiar with, sine, cos and tan. They apply to right angled triangles. But often in real life you have situations involving other triangles and you need some other rules to solve missing sides or missing angles in those. So jot that down in your notes, pause the screen, and moving on. So you've got the sine rule. Now, importantly, you've got the sides of a triangle, any triangle, labelled A, B, and C. And then you've got the angles labelled with big A, big B, and big C. So uppercase for the angles, lowercase for the sides to distinguish them. And importantly, you've got opposite pairs. So angle A is opposite side A, B is opposite B, and side C is opposite angle C. So in any triangle, says the sine rule, A over sine A, so that's side A over the sine of angle A, equals side B over the sine of angle B, equals side C over the sine of angle C, where side A is opposite to angle A, etc. So in order to use this, you need to know at least one of the pairs. You need to know, for example, both A's in order to evaluate anything with any certainty. So here's an example from the book. You've got 15 centimeters, two of the angles, 32 and 46, and you've got to find x. So because you know this opposite pair, the 15 and the 46, you can use the sine rule to say x over the sine of 32, this side over the sine of the opposite angle, equals this side over the sine of that angle, 15 over sine 46. To figure out what x is on its own, you want to get rid of this fraction, so you multiply both sides by the denominator, which is the sine of 32. So x becomes 15 times the sine of 32 over the sine of 46, which looks complicated, but it's something you can evaluate on a calculator, and it's 11.05 to 2 decimal places. So there is an ambiguous case of this that you need to be careful of. So for example, in triangle ABC, AB, so that's the length from vertex A to vertex B, is 10 centimeters, from B to C is 7 centimeters, and angle CAB, so that's the angle at A, is 42 degrees. When you try to construct this, you find that there's two possibilities. So I draw the 10, I measure the 42, and then I know that side C has got to be 7 centimeters away from point B. So I get my compass point on B and I measure 7 centimeters to see where it hits the line. And there's two places where it hits the line. So from the information that we were given, there were two possible ways you could construct the triangle. You could construct it like this one I'm just highlighting here. So 10 centimeters on the base, 7 centimeters from B to C, and 42 degrees at A. Or you could construct it like the one I'm now outlining it. That's also 10 centimeters on the base, 7 centimeters from A to C, and still 42 degrees at A. So two possible places where C could go. I've labelled them C1 and C2. So that's called the ambiguous case of the sine rule, because when you construct it, there are two possible solutions. It is ambiguous. So that's related to the fact that when you do the graph of sine, it's not a one-to-one function. So there are many values that could have a sine of 0.5. So 30 degrees could have a sine of 0.5, but also 150 degrees could have a sine of 0.5. So on your calculator, if you do sine 30, you get 0.5, and if you do the inverse sine or arc sine of 0.5, it'll take you back to 30. But it won't tell you all of these other values, 150, 390, an infinite number of other values that could also have a sine of 0.5. So it's only telling you just zoom in on that, your calculator only gives the primary value of sine 30. Okay, so when you try and do that on the calculator, for the triangle we were talking about earlier, you get sine c over 10 equals sine 42 over 7. Oh, by the way, yes, so the sine rule is quoted as a over sine a equals b over sine b equals c over sine c. It would work just as well if you flip those. In some circumstances, it might be just as easy to do that, and it might be helpful to do that in terms of simplifying the algebra. Okay, so in the triangle we had, you do the sine rule on it, it comes out to be that the angle C is 72.9 degrees. So going back to this here, it tells us that the angle C is 72.9 degrees. That's the angle at the top. And clearly, looking at the diagram, this one looks more like 72.9 degrees than this one, which looks obtuse. But looking at the sine graph, another angle that could also have a sine that's the same as 72.9 degrees is the angle 107.1 degrees, because they're both symmetrical around 90. So the answer we got from the calculator, 72.9 degrees, is how many degrees? 17.1 degrees away from 90 going back. So another possible angle is 90 plus 17.1, because of the symmetry of this, is 107.1. So you could also have an angle C being 107.1. And looking at the diagram that we constructed, oh, in fact, there it is. So 107.1 down there and 72.9 up there are two possibilities for what angle C could have been from the information given. Okay, so there are some examples from the book, and that was the question one was the example I just ran through. I've also got another video for this proving the sine rule, so you might want to check that out. Okay, and then we've got the cosine rule. So to use the sine rule, you need to know that opposite side and angle pair, but you don't always have that information. So if we know two sides and the angle between them, then we can use this rule, the cosine rule. A squared equals b squared plus c squared minus 2bc cos a. The big A there, I've made a different colour, that sort of purpley colour. That's an angle. All of the others are lowercase and their sides. So the important thing there is you can get away without knowing an opposite pair. As long as you know enough other information, it doesn't have to be an opposite pair. So for example, in this triangle, you've got a 4, a 5, you've got the angle between them, which is 32, and you want to know the side opposite the angle. So for the cosine rule, you need to know two sides and an angle between them. So I'm going to label the angle that I've got as being A. Then the side opposite that we're trying to find out is going to be side A with a lowercase, and then the B and the C are going to be 4 and 5. Doesn't really matter which way round you label those. If you look at the equation here, you could put the B's and the C's in each other's place and it wouldn't make a difference. So putting all the numbers in, you get x squared equals 5 squared plus 4 squared minus 2 times 5 times 4 times cos of 32. That's just a squared equals b squared plus c squared minus 2bc cos a. Stick all the numbers in. We've got all the numbers, so it's something we can actually evaluate down to x squared equals 7.078. X is the square root of that, 2.66. So in this triangle here, x is 2.66. So that's finding a missing side. Quite easy, just stick all the numbers in, assuming you've labelled it correctly in the first place. So the angle that you've got, you're labelling A, big A, for the purposes of sticking the numbers in this formula. And then the two sides that the angle is in between are B and C. And once again, it doesn't matter really which way around you label those. That's a missing side. Example 2, finding missing angle. So let's say we're missing this angle there, which I've called Greek letter theta. Then the side opposite it is going to be labelled as A, that's 6 in this case. And then the B and the C are the two sides that have the missing angle between them. Again, doesn't really matter which way around you label those. There's a certain symmetry to the B's and the C's, so that doesn't matter. But you've got to label it correctly. So again, we've got a squared equals b squared plus c squared minus 2bc cos a. So the A is what I'm calling the Greek letter theta for the purposes of this. The B and the C are 9, and the little a is 6. So sticking all of that information into the sine rule, we get it down to 145 equals 180 cos a. Dividing both sides by 180, 145 divided by 180 is cos a. So we just inverse cos that fraction to find out what a is, and it comes to be 36.34 degrees. So a, or theta, I should have called it, is 36.34 degrees. So do pause the screen, take notes from this, and check that you understand every stage of the calculation there. Okay, third thing, area rule. For any triangle, the area of it can be calculated from a half AB sine C. So a half times the product of two sides times the sine of the angle between them. So in this case, if you've got a 7 and a 9 with a 45-degree angle between them, that uniquely identifies this triangle with no ambiguity, and you can work out its area from sticking those numbers into this formula, and it comes out to be 22.3 centimeters squared. I have got separate videos, do watch explaining these, or not explaining these, proving these results. So I'm not asking you to take these just on trust. I have got some videos that you can watch proving these, the sine rule, the cosine rule, and can't remember if I've done one for the area rule, but I'll have a look.